Okay, everyone, let's get started. So today we are going to be talking about a couple of related topics. We'll start with just providing a quick overview of retrieval and how retrieving relevant documents to a particular input can help improve the output of the language model. So this has been studied starting with models like BERT. How can we integrate retrieval to make better predictions? As we'll see later on in the class, it can also be useful in the context of prompting, where I might have a question, the model doesn't know the answer, so it retrieves some relevant information from, say, the internet or from a collection of books, and then it's able to reason over that information. All right, so let's take a look at retrieval augmented language models first. So in this case, I want to just make it clear that there's a division of knowledge between parametric knowledge, so what is encoded within the parameters of the language model itself, and external knowledge that is encoded within, say, the internet or unstructured text and is not captured by that language model. So as an instance of the former, hang on, let me just close this. As an instance of the former, let's take a look at this example here. So we have Bob went to the mask to get a buzz cut. And if you pass this to BERT, obviously the goal of BERT is to predict a distribution over what could be in that mask token, that location. And so maybe barbershop has 54% probability, barber has 20%, and so on. So clearly the model has learned, in this case, something about the world, right? That if you want to get a haircut, you should go to a place that cuts hair, like a barbershop. So this quote is from the Realm paper, which is one of the assigned readings. And it makes this point that the language models learn some world knowledge that is stored implicitly in the parameters of their, this big transformer network, right? So in this case, the model knows that haircuts occur at barbershops, right? It doesn't need to be told this information via a prompt or some retrieved examples. It already knows it. But some other information it might not have picked up during training, or what happens with text that is created after the model is trained, right? The model has no knowledge of current events or things like that. So really the whole point of these kinds of retrieval augmented model is what do you do when you train a model once? It may not perfectly capture all of the important knowledge in the pre-training data set, and you don't want to retrain it again and again as new information occurs, right? As new events happen in the world and new words are made up and new trends occur, right? You want the model to be able to adapt to this changing environment without spending millions of dollars to retrain the model. So the whole point of retrieval-based adaptation is, can we just allow the model to reason over new pieces of text that describe events that it has not already encoded in its parametric knowledge? So that's what this is saying. To capture more world knowledge, one must train ever larger networks, which is slow and expensive. So we would like a way to avoid this state of affairs. And so in the Realm paper, they propose a very simple approach to augmenting the language model with an external retriever module. So let's say I have this example, the mask at the top of the pyramid, and I want to fill in the mask token. So here, you have to have some domain-specific knowledge to know what the thing at the top of a pyramid is called. And so maybe the model doesn't know this, and so it then is able to retrieve from a huge data set, let's say the internet or Wikipedia or Google search. It's able to use this text as a query to retrieve any relevant document to the query. So maybe it retrieves a bunch of documents about pyramids, or a bunch of historical documents or something like that that could be useful in filling in the mask token. So one of the documents it retrieves might actually have the correct term. The pyramidion on top allows for less material higher up in the pyramid. This could just be part of some document that was retrieved. So now obviously the model's job of filling in this mask token becomes a lot easier, right? It has some direct evidence suggesting that this word is the thing that should go into the mask token. So once you retrieve some relevant articles, what you can do is just concatenate the text of the retrieved article to your original input. So my original input here was the mask at the top of the pyramid. So I'm going to form an input to BERT. So I say the mask at the top of the pyramid. I have some separator token to indicate that now I'm going to, provide text from an evidence document, and then I'm going to proceed with the evidence document. The pyramidion on top allows for less material. So now you would expect the model to give a much higher probability to pyramidion in the mask token than maybe it would before. Does that make sense? So in this case, we are allowing the model to query an external knowledge source to find information that could be useful for solving its objective. So you'll note that if you train a model like this, the model may not ever encode knowledge about the pyramidion in its parametric knowledge, in its pre-trained parameters. Why might it be discouraged to encode this kind of knowledge within its parameters in this retrieval augmented setting? Any ideas? Okay, so we can take some time to listen to that. Okay, maybe I'll ask the question again. They're getting louder. Maybe they're chanting the answer. Okay, let's say I have this setting, the BERT setting, without the retrieve document. The pyramidion at the top of the pyramid, right? So I mask pyramidion, and I'm training the model to increase the probability of pyramidion. In this case, the model has access to no external information, and so if it's going to learn the fact that the pyramidion is on top of a pyramid, it has to encode that into its parameters somehow, right? Otherwise, there's no way for it to learn that. What I'm asking is, in this setup, is it as necessary for the model to encode this kind of knowledge in its parameters? Exactly, so it's a good answer, right? The model, in this case, does not need to understand that the pyramidion is at the top of the pyramid, because it might learn that it can rely on its retrieval module to provide this kind of information, right? And this is kind of similar to how we operate, right? I can always look up a specific term or something like that. There's no need for me to memorize every possible thing. That's also, good advice for your midterms, right? You can look up or ask the AI or whatever. So this approach is a little more flexible, right? Because now the model is not bound by just encoding all the knowledge it's ever seen in its pre-training data in its parameters. It can rely on this external retriever module. Yeah. Yeah, so is your question, how do you implement? Oh, sorry. Yeah. Yeah, so this is a great question. This is all great if this retriever function is actually providing relevant documents, right? If this function is providing irrelevant documents or things that are misleading actively, then this could actually hurt the whole process. Do you have a question?
Just to clarify, is it using the retrieval during training?
Yes, so this approach does use retrieval during training, which is enormously expensive. I'll cover how they actually make it work in practice in a couple slides. But back to your question, how could we implement this retriever? So you know, there's a whole field of information retrieval that comes up with various methods to retrieve given a query against a huge search corpus. So for example, like Google search is doing retrieval, right? So how does that work? Basically, there are simple approaches which map keywords from the query to keywords in the actual document. So in this case, like pyramid is a very important keyword. So obviously any document you retrieve should have the word pyramid in it somewhere, probably. As you suggest, the compositionality of this phrase is very important, right? You're specifically interested in what is on top of the pyramid. You're not interested in any other aspect of the pyramid. So these kinds of keyword matching approaches kind of break down in this case because, you know, at the top of these are all very frequently occurring words. They're unlikely to be useful with keyword matching compared to a more rare word like pyramid. So that motivates a more complex kind of retrieval function. So let's just take a look at the retrieval function. I'll get to it in a couple slides. So just to break down the probability here, if we're interested in the probability of the mask token, it's usually, and let's say this mask token, the word that it actually goes into the mask token will represent with y, right? So y is a distribution over the entire vocabulary. And X is our input here, the mask token at the top of the pyramid. And Z is going to be our retrieved document. So basically our probability of Y given the input X, which is what we saw in our normal BERT model, is now incorporating this Z, which is the retrieved document. So if we have multiple retrieved documents, then we might want to marginalize over the set of top K retrieved documents or all of the documents in our search collection. And these are weighted by some probability of how relevant the document is to the query that we have. So you can see here that PZ of X is giving us the probability of any document given the input X. So let's say, for sake of argument, that all of my documents are from Wikipedia. So each document is a Wikipedia article. And I have an input query X, and so I'm now going to compute a probability of how important that document is to my, my query for every single one of these Wikipedia articles. So that's what this P of Z of X is doing. So now back to your question, how do you actually implement this retriever, this P of Z of X? You can see that in the formulation in the Realm paper, it's not a simple keyword lookup, but they're actually using BERT models to do this retrieval. So intuitively, you can imagine I use BERT to produce a vector embedding of my input query. So I have one vector for the input, which is the mask at the top of the pyramid. That's been encoded into the vector. And then I have one vector for every single one of my documents. In every Wikipedia article has its own vector that I get by just passing the document into BERT. And I can take like the CLS token, for example, for all of these to get just a single vector. So now, given I have a single vector for my input X, and I have a ton of different vectors, one for each Wikipedia article in my data set, I can take the dot product between my input vector and each of those article vectors. And the idea is that documents that that are more relevant to my input query are going to have a higher dot product than documents that are less important. So this approach, if you kind of follow the intuition, would kind of allow you to get at these highly compositional queries as long as the BERT model can understand the meaning of that, like the semantics, and encode it into the CLS vector. So in this work, they use BERT as the embedding function, and they use BERT to do retrieval. This kind of approach is used in Google search for ranking articles that are relevant to your query as well. So before BERT came out, Google search was powered by more like keyword type ranking algorithms, but now it is powered by deep learning models. Okay, so let's move on then. I think the encoder here is, yeah. Yeah, so you can compute the relevance for any arbitrary query as long as you have a way to embed the query, right? So I could have create a different example, the pyramidion at the top of the mask. And similarly, I can embed this into a vector and then compute the dot product between that vector and my entire data set of articles. If I mask the word the? Yeah. Okay, so you're asking about the masking strategy. So I won't talk about that, but in this work, they don't randomly mask all words. They only mask like important salient entities and numbers, because these are things that are much more likely to have useful results when you do retrieval. So that's a great point. Yeah, yeah. So in this paper, they use the pre-trained BERT model to initialize these embed functions. But you could train everything from scratch. It's just very expensive. So of course, like if you're using the embed function to model the semantics of the input query, you already get a lot of that from the pre-trained BERT model. Okay. I think going to your question, isn't training this retriever extremely expensive? Because if you look at this formula here, you have to sum over every single document in your training corpus, which is, in our example, every single Wikipedia document in order to get a valid probability distribution, right? So obviously this is highly expensive, and one interesting aspect of this whole problem is that we don't know which documents ahead of time are actually useful for making the probability of, say, pyramidion increase. So this paper was done by Google, so they had a huge amount of resources. Even they had to do some approximation in order to get this to work. So they note that the challenge here is that summing over all of the documents is intractable, because you're at every batch you're masking some words, and you're retrieving for every single example in your data set. So if you're going to be summing over every single document, this is hugely expensive. So what they do is they approximate this by only summing over the top K documents, where K, I forget what K is, it might be like 8 or something like that, but something very small. And they note that this is reasonable if most documents have near zero probability, which could be true for a majority of queries, depending on your value of K. So the other part of your question is, how do you actually update this retriever, right? Because it's very expensive if you're going to train the retriever along with the masked language model. At every step, you need to backprop through both the retriever as well as the base language model that you're training. So what they do is they actually do asynchronous updates. So they take a copy of the retriever and they'll use it for several hundred updates for the base language model. And then they will update the parameters of their retriever again and recompute the entire data store, so all of those vectors, right? Because if you update the retriever at every time step, you need to recompute the embeddings for your entire, like all the Wikipedia articles, which is a huge time sink. Yeah. So if you keep the retriever fixed, it might not learn things like what she was saying about on top of the pyramid, you probably want to retrieve very specific articles for that instead of more general articles. So training the retriever allows the model to actually learn what aspects of the query need to be modeled in this particular masked language modeling setup. You could use a pre-trained retriever. In fact, nowadays people do tend to use pre-trained retrievers instead of ones trained like this. But yeah, both are options. Yeah.
So before the retriever is fine-tuned, it like probably is not going to retrieve anything that has any sort of notice.
That's not true because it depends on how you initialize the retriever. If you use a pre-trained BERT model, then the retrievals at the initial stage are probably already at least somewhat relevant. Like you might expect to get articles about pyramids, for instance. But, yeah. These are all BERT models, but they're separate copies of so they don't share parameters. Other questions?
So I will more share about the efficiency of the distributive functions and because then I realized that we use a lot of distributive functions and the free can make the efficiency much higher, and with the concept of augment, I think we can.
Yeah, so the question is about the efficiency of the retriever and how important is it. It is extremely important, and there are many people who are working on more efficient retrievers so that they can be incorporated into language models in this way. There are several approaches that are extremely inefficient, and so even though they result in better quality generations, they're just not practical to deploy at scale of GPT-4. Yeah, there are lots of people who are thinking about better approaches to retrieval. Yeah, I can point you to some after class if you're interested. Other questions? Yeah, so I think you're talking about real-time information, right? So there are, for example, say Bing Chat or Google's Bard. These are models that are conditioned on real-world, real-time information. We'll take a look at how they do that, but it's much simpler than this. Essentially, they already have all these feeds of real-time data, right? And what they do is they just dump the information from the real-time streams into the prefix of the language model. And you can, kind of massage that with various prompt engineering techniques like we will see in a bit. But they're not doing anything related to the model itself. And, that could be an issue because the model may not know how to use the retrievals because it wasn't pre-trained with them. But perhaps with some human feedback tuning, it could learn how to do that. And I suspect that's part of what they're doing. All right, let me look at these YouTube questions. The LLM loses its purpose if it is, I think this is an answer to the questions. Hello, hope you are enjoying some tea today, Doctor. Okay, I am indeed drinking tea. All right. Do you only choose one text when calculating the loss? I assume this means the query text, in which case remember that these are batched training, so you have many queries in one batch and you're doing the retrieval for every example in the batch. And you also obviously choose multiple retrievals per example. You choose the top K retrievals for this. Okay, and just one note to your point about efficiency of the retrieval. We don't actually compute the exact dot products between the query and all of the Wikipedia article vectors. Instead, there's a class of algorithms that approximate this nearest neighbor search and approximate the maximum inner product search. These are called MIPS, and there's a library that is not on this slide called FAISS, F-A-I-S-S, that was released by Facebook, and it has a ton of these algorithms that are highly optimized. A lot of people use that library for efficient retrieval with these language modeling settings. Okay, so I talked about refreshing the index. Sorry, I'm going a little quickly because I want to get to the other stuff that we have too. So let's take a look at how retrieval actually helps performance. So in the Realm paper, they evaluate on open domain question answering. So this is, the questions are kind of similar to the ones we saw in Squad, right? Like who was the main actor of the Matrix, but we don't have any supporting documents. So the model is expected to either have already encoded the knowledge of the answer within its parameters, so this is the parametric knowledge, or it is supposed to access the external data, perhaps through retrieval, to figure out what the answer to the question is. So here's a table from the paper. This is the BERT base model that has access to no retrieval, no external data. It's just the pre-trained BERT model. And it's scoring about 26 on this natural questions data set. And you see here the Realm paper, which is using this dense retrieval. Oh, sorry, I should say that this BERT one is using a very simple retrieval in addition to the BERT model, but the retrieval function is not learned. And in the Realm paper, we observe that the X here is the retrieval corpus. So it is retrieving over the Common Crawl, and the Z is from Wikipedia. I'm not actually sure what these terms are. So its pre-training data set is either the Common Crawl or Wikipedia. But you can see that the performance on this natural questions data set is significantly higher than the standard BERT model, with 3 times as many parameters, but the performance gap is huge. So this gives you an idea of like the kinds of improvements you can get with retrieval. And here's a specific example. So an equilateral triangle is easily constructed using a straight edge and compass because 3 is a mask prime. So here the goal is to fill in this mask, which is also kind of answering this question, right? Like what kind of prime is this? So the correct answer here is Fermat. And we see that the BERT probability here is very low, 1 times 10 to the negative 14th. But when you use Realm, the probability of the correct answer goes up to 100%. And you can see that the document here is clearly stating that, it at least states the answer within a similar context. When you marginalize over the top 8 retrieved documents, you still get a much higher probability than you do with without any retrieval at all. So this example is basically showing that BERT, the pre-trained model, did not encode this knowledge into its parameters. And so allowing it to access external information, it makes it able to take advantage of knowledge that is external to the model itself. All right, any questions on this? Yeah.
Is the query coming from the same distribution as the documents?
The query here is anything except it has a mask token in it. So that makes it kind of look a little strange compared to the documents.
So I think in the last slide, the X was the distribution of the queries.
Okay.
And Z was the distribution of the documents.
So the queries are all coming from the data set here, natural questions. Yeah, so those I think could be reformatted into these kinds of masked language modeling examples. Yeah.
So we are masking tokens, but the answers to questions can be at least 2 words or 2 words more.
Yeah, so in this data set, the answers are all just entities or numbers. But yes, this is a big problem for generative QA tasks where the answers may be longer. We'll see some examples of that later on in the class. But this method is not good for those kinds of tasks because it's using a BERT model, right? BERT models are not good for generation at all. So yeah. Okay, so let's move on. So I just wanted to quickly introduce, just following on to your question, a task of long-form question answering, which we will then look at within the context of prompt engineering. So in the past, I've done much more on this topic, but I think at this point, it's more interesting to look at this task as one that could be a test bed for various prompting techniques. So in this task, unlike the QA example we just saw from natural questions, you are asked to generate a long-form answer to a question. So here, why do humans need to eat many different kinds of foods to get their vitamins, but cows only need to eat grass to survive, right? This cannot be answered by a single word or a single number, right? You have to generate an explanation that is understandable to some lay reader. So you can see that the answer here is multiple paragraphs long, and some of these can be very long. So this task usually involves both retrieval and generation. So with weaker language models, you just assume they don't have enough knowledge about the topic in order to generate a very coherent answer. And so you would like to retrieve some articles, like maybe about the cow's digestive system and the human digestive system, and you would like the model to condition its generated answer on this information that hopefully is very relevant to the question. So basically, this scenario is much closer to what things like Bing Chat or Bard are doing. So you have a question, you then look up that question on, say, Google search, you get a bunch of relevant documents, you take text, like snippets from those documents, and put them into the prefix of your language model. Then you put the question in, and then you say, you know, like, generate a complete answer to this question and use the evidence documents as support to support your answer. So this is how all of these new like search engine language model hybrid systems work. They're not doing anything fancy. They just train the language model first without access to the internet, and then they kind of bolt on this information that comes from Google search or Bing search afterwards. Okay, so there are many issues with this task of long-form QA. If you think about it in the context of a train dev test set that I wanted to highlight here, just because many of you might encounter similar issues with your own projects. The first is that obviously when we're doing any machine learning task, we want to test the model's generalizability to new inputs that were not present in the training set. This is very hard to do for long-form question answering because or other tasks, because you can ask the same question in a variety of different ways, right? So this question here, can you protect electronics from solar flares? If so, how? This is a question from the validation set, right? The dev set. But in the training set, there are many, many very similar questions that are phrased differently. Like, how does an EMP ruin electronics? What does it do? How would they be fixed? Can it be protected against how, right? This is, the answer to this question is also an answer to this held out question. So this overlap is especially bad in these retrieval augmented settings because imagine you train this model that retrieves and generates answers on the training set. And now you get this question. Do you think the model actually needs to use its retrievals at all in order to answer this question? The answer is no, because the model has already seen many versions of this question before in its training set. So the easiest way for it to answer this question is just to copy one of the training answers, and that's much simpler than learning how to reason over some retrieved information. So it's very important to check for paraphrases in your training, validation, and test set to make sure there's no overlap there. Also, another challenge with this task and with many other generation tasks, as we discussed last time is evaluation. So we talked about the Rouge score, which is commonly used for long-form QA evaluation, even though it doesn't make sense for this task. Remember, Rouge is looking at how much text in the reference overlaps with the generated text, right? But in long-form question answering, there are many possible valid, plausible answers that you can write in response to the exact same question, right? And so this kind of scoring an answer compared to a reference doesn't make sense like it might in summaries or translation. So like human evaluation is very important for this task. Okay, so this was the output of our state-of-the-art model, which was back in like 2021. Why are almost all boats white? So it says boats are painted white for obvious reasons. This is so obvious that the person asking it, like, why would they even ask it, right? As they are inexpensive and easy to clean. Yeah, not sure what that means. Ships are also often painted white to provide a visible visual contrast to the sea. That seems a little more reasonable. But then it says boats have an air-breathing function that makes them easier to spot and stay afloat, which is a good thing if you're a pirate or trying to get into some country's waters. This is completely irrelevant, also not true, I imagine. And then you see the highlighted text here. There are many, many more reasons for why ships are white, but those are the ones I know of. I'm sure there are many other reasons, but those are the ones I know of. Edit, I forgot to mention, and then it repeats itself again. So you can see that if you train the model on like Reddit, then it learns these kinds of common Reddit posting behaviors and outputs them. And the answer itself is not too great. Okay, so I wanted to now turn to some prompt engineering techniques and use this task of long-form QA to demonstrate many of the most recent strategies for prompting large language models. So remember that when we discuss like a large language model, here we're not talking about things like BERT, but rather huge scale models like GPT-3, or now we have GPT-4. We don't know exactly how big it is, but it's probably pretty large. And we can apply strategies to these models that don't work with smaller models. So the reading for today included a blog post that goes over many of the most commonly used prompting strategies today, and I'll go over some of these through examples. So let me just make sure I'm connected to this. So this is the playground here for GPT-4. I assume this text visible in the back. Can you read it? Okay. So let's just say you are a helpful assistant. This is like the default message for these things. And now I've written up some prompts with various prompting strategies. So we already talked about zero-shot and few-shot prompting. So I'll start with that in the context of this, this task. So this is a zero-shot prompt. Explain like I'm 5. Is there a scientific reason not to shower during a thunderstorm? I've given the model no training data, right? I have given it no examples of the format of my output. I haven't given it instructions on how lengthy of an answer it should generate or how it should structure the answer. I'm just giving it a question and hoping that it will give me a good answer. Let me adjust some of these things here. Sure, just to make sure it doesn't get cut off. And I will submit this. And it says, imagine you're playing with a toy car that can carry a marble. A thunderstorm is like the marble being dropped onto the car from a height. That's an interesting analogy. The car is your home and the marble is lightning. And when lightning hits your house, it can travel through water pipes, and if you're in the shower, it could reach you just like the marble reaching the car. So better not to shower during a thunderstorm to stay safe. Wow, I would have expected a better answer here. But you can see that it actually took the explain like I'm 5 part pretty seriously, I guess. Maybe 5-year-olds can only understand cars and marbles. But now let's take a look at a few-shot prompt for the same question. So here in a few-shot prompt, remember that I'm going to give the model one or more examples of the task, like example inputs and outputs, along with the question that I wanted to actually solve. And so these input-output pairs in the few-shot prompt are called demonstrations, because I'm demonstrating how the model should behave given a particular input. All right, so let me just paste this in here, and then we can read it over here. Okay, so here I have this demonstration question. Explain like I'm 5. Why does the amount of protons in an element wildly change its properties? For example, why is 2 protons a gas, but suddenly 3 protons is a metallic solid? The answer here, you can see, is multiple paragraphs long. It has this kind of analogy to a simpler situation with buildings and rooms. And it has some sort of summary paragraph. So it's quite a lengthy answer, right? And hopefully, when I now ask this question, is there a scientific reason not to shower when there's a thunderstorm, the model is not going to output something about marbles and cars, but maybe it outputs something that is a little more detailed. But we'll see. I did not observe this marble and car answer before, so I actually have no idea what's going to happen. All right, so it says, yes, lightning can travel through pipes and wires in your home. If you're taking a shower, the water in the pipes can conduct electricity from the lightning and you might get an electric shock. That's why it's safer to avoid showering when there's a thunderstorm happening. So it did kind of change the, the writing to match the audience that it might be expecting from the first demonstration. But you can see that it didn't copy the entire template. Like this demonstration has an answer that's many paragraphs long, and GPT-4 generates a single paragraph answer. That's not to say that it'll do this every time, right? These models are not deterministic unless you're using greedy decoding, right? So if I took another sample, let's see what happens. Oh, maybe it will. So this is a different answer, right? Lightning is a big and powerful electric spark. Now it's generating another paragraph as well. The language of this answer seems simpler as well. So you can get multiple answers, and one interesting property of this is that some of the answers may contradict each other, right? So the model, if you take enough samples, you might see some samples that are like, oh, showering during a thunderstorm is perfectly okay, right? Or many different reasons for why it's not safe that are included in this answer. So there are some strategies that we'll talk about a little later that take multiple samples in and figure out how to aggregate those answers into a single one that hopefully is better than any of the individual answers. Let me see if we have any questions on YouTube. Is it possible that the answer just sounds correct and is not actually correct? Yes, I think that's a big problem with models like GPT-4, is that the answer might sound very reasonable, but unless you have some attribution of like this part of the generated answer was a result of reading this evidence document, you have no way to easily verify that unless you're an expert in the domain. But if you ask GPT-4 a question, it's probably because you don't know the answer already, right? So evaluating its output is very difficult. That's why later on in the semester we will talk about attribution in these large language models, where you might have a language model generating text but also citing its sources and maybe even linking text that it generates to specific spans of human written documents that provide that kind of support, so people can trust the outputs of the models some more. Anyway, that's an aside. So far we've talked about zero-shot and few-shot prompting. The next thing we're going to do is look at a different way of doing few-shot prompting. So in this case, I just picked a completely random question and put it in as a demonstration to the model. But you can imagine that maybe if I have a large set of potential demonstrations, it might make sense to pick demonstrations that are more similar to the target question instead of just picking any random question. Right, so this question has to do with like protons and elements. This question has to do with thunderstorms. Maybe if I took a demonstration whose answer is already about thunderstorms, I would have a better answer. So there's a class of techniques that involve retrieval just for the purpose of prompt demonstration, like finding the best demonstrations to maximize the quality of the output answer. So we talked about retrieval for making like a BERT language model produce better predictions of the mask token. How do you think we could use retrieval to get better demonstrations when we're doing few-shot prompting with a language model? Any ideas? So let's say we have a target question, like, is there a scientific reason not to shower during a thunderstorm? And I want to retrieve all similar questions in some data set that I have so that I can put the top K most similar questions and their answers into the prompt as demonstrations. How would I implement that? Yeah, exactly. So that's exactly correct. I can use the exact same method that I just talked about with the realm retriever, right? I can encode all of the demonstrations in my training data set, like the QA pairs, using BERT into individual vectors. I can then encode this question in as a vector and do the nearest neighbor mapping to find the QA pairs with the highest dot product to my query vector. So this general setup of encoding the query and encoding all of the possible evidence documents or demonstrations or whatever you want to retrieve over as vectors and then doing a fast inner product search is generally useful for so many different applications. And you should make sure to understand why that's useful and how it's implemented, because all of them are basically doing the same thing. You implement, you get from text to vector using a pre-trained BERT model, and then you do some, fast inner products search. Yeah, that's a good point. I think in some cases you will encode just the question, probably in most cases, but you could imagine the answer also could have some overlap with terms in the target question, so it might be useful to encode the answer as well. But yeah, there's multiple ways you could think about that. Okay, so in this case, like I just used Google to find a relevant question. Whoops, not this one. But in practice, you would use some sort of retriever method. So here you can see that this question, explain like I'm 5. Why aren't planes affected by lightning if they are made of conductive materials? So you can see that there's some overlap between this question and the one that I actually want to answer about thunderstorms. So ideally, I would have a retrieval method that would give this question a high score, and then I could put its this question and its answer in as a demonstration. So one limitation of this approach is that I need to have a very large set of demonstrations, right? Each demonstration is a question-answer pair in order to make use of retrieval. Why might this be? Like, why would I need a large set of demonstrations? Exactly. So if I don't have a large, diverse set of demonstrations, then I might not have any questions that are about lightning or thunderstorms or anything like that. And so retrieving doesn't make sense. If I have 5 demonstrations, then I'm not going to be able to use this technique, right? I'm better off just putting all 5 demonstrations into my prompt as few-shot examples. So this kind of retrieval-based demonstrations in the prompt is only useful when you have a very large set of examples that you can use as demonstrations. So these have to be labeled, right? I need a question and an answer because the model needs to know how to behave given these questions. Okay, so let's see what happens here. I doubt it'll change much since this question is probably too simple for something like GPT-4. But we'll see more complicated examples where it's very clear that the model is actually using the retrieval, is using the demonstration. Okay, so that's just a modification of few-shot learning that if you have a large set of demonstrations, you can choose the demonstrations dynamically depending on what the target question is, rather than use the same few-shot demonstrations for every question. Does that make sense? Yeah.
You can even use this when you already have some few-shot examples to further retrieve more similar few-shot examples. Like not only in the zero-shot setting, but it could be even in a few-shot setting to augment the number of examples you pass on.
Yeah, you could certainly use it to, if you wanted to have some fixed examples that are the same for every target question, and then you have, some retrieved examples, you can certainly do this. Yeah. As an aside, you can also combine this method with prompt tuning. So note that all of these methods are not doing any sort of training on the underlying language model, right? They're just modifying what goes into the prefix of the language model. But we talked about prompt tuning, which actually learns these embeddings that based on the target task. So these two approaches are actually complementary to each other. There is an approach called instruction prompt tuning, where you put the learned prompt embeddings at the front, and then you have a natural language instruction, possibly with some demonstrations, and then you have the target example. So you take advantage of both whatever the model has learned in those prompt embeddings that's useful for the task, as well as perhaps some dynamic retrieval of similar examples. So this approach is what you would do if you wanted to maximize your performance on a downstream task, and you have a lot of demonstrations for that task. So you have a lot of labeled data. Approaches like prompt tuning are not feasible when you have almost no labeled data. They need a training set to learn the embeddings. Okay, let me check on YouTube. It looks like no other questions. Let us then continue with our next thing. So we talked about instruction tuning, right, with the Flan model and data set, where they collected all these instructions that were paired with different tasks, and they fine-tuned a language model on instructions and found that they were able to generalize to new instructions. Instruction prompting is you just describe your task in natural language instructions and see how it, see whether it follows those instructions. And you should note that models like GPT-4 have been instruction tuned already, and they've been tuned to follow instructions via human feedback as well, through like the reinforcement learning from human feedback. So they've already seen many examples of, I want you to do exactly this, given this input, and that's why they're able to generalize to arbitrary examples. So here, I gave the model of this example instruction: answer the below question in 4 paragraphs. Please be as detailed as possible while also ensuring that the answer is easily understandable by a lay person. Make use of illustrative examples and or analogies in your answer. Then here's our same question. Explain like I'm 5, is there a scientific reason not to shower during a thunderstorm? So let's see if it actually follows these instructions. Think of lightning as a giant electrical zap from the sky that can reach the ground in a split second. The energy from this zap can be strong enough to cause severe damage or even harm people. Imagine electricity riding a water slide. Okay, so it has, like this analogy to a water slide, right? Which hopefully can help people who don't understand this topic at least make some sense of the answer. seems like it's also 4 paragraphs long, which is what I put in the instructions. So you can see that of all the techniques that we've tried so far, this seems to be the best at controlling like fine-grained properties of the output, right? In the few shot case, I gave it a demonstration that had multiple paragraphs for the answer, and yet it still produced a very short answer. In this case, it produces 1, 2, 3, 4 paragraphs, exactly like I said. It had a lot of detail. It made use of analogies and examples like this water slide. And overall, it's probably a good answer. I'm not going to read the whole thing, but so you can see the power of adding some natural language instructions to these models, right? Perhaps this is a good way to go to actually get them to do what you want. Yeah.
Can you understand the instructions from the feature example? So if we mention in the feature case that have a similar format instructions to give out the paragraph.
Yeah. So that you can view as an instruction, right? Like,
so you're able to generalize that paragraph and figure out what instructions you could have in the workplace.
I wouldn't be surprised if it mapped like the length of the demonstration answer to the length of the output answer, but it's hard to say. And in many cases, so we're talking about what is called prompt engineering here. These are some techniques for essentially getting the best quality outputs out of a black box language model. This is also like a new type of job. I don't know if people have seen, but there are many job ads now for prompt engineers that actually pay like huge salaries, and all you're doing is literally like, okay, I shouldn't say that, but like, I mean, like really, you're changing a couple words in the prompt and trying to figure out what the model is best able to understand. And so like what you suggest is just one alteration of this prompt to see if the model gets a better understanding of what it's supposed to do. It could be possible, but these are all like very difficult questions to answer if they're useful or not, because we have no access to the model or its pre-training data or its human feedback tuning data. Okay, so that was instruction prompting. And now I wanted to talk about something closer to what we were discussing in the first half of this lecture, which is retrieval-augmented language modeling. So here, let's assume we have an external retriever that is already, like say Google search, right? We can give a query and get an output. So let me just paste this in here. Maybe first I can show you this article that I found when I just Googled this question. So there's this article, why it's not safe to shower during a thunderstorm. It's, you know, a couple paragraphs long. It has some information from the CDC, some official quotes and stuff like that. So let's say that I have retrieved this article using some method. Either I Google searched it or I have a learned retriever that I trained myself and it found this article to be very relevant to my question. So now I can use this in my prompt by doing something like the following. I can mix my instructions with the evidence and see how it behaves. So let's look at this prompt. Read the below question and evidence document, then answer the below question in 4 paragraphs. Please be as detailed as possible while also ensuring that the answer, blah, blah, blah. It's the same thing as before. I also added this part. Make sure that your answer includes verbatim snippets, so like parts of the evidence that are copied into the answer, or summaries of salient content from the evidence document, and that it cites the evidence at least twice. So now I'm asking it to write things in the answer and also cite the evidence document. Of course, like I haven't specified how it should cite the evidence document, so I don't actually know what it's going to do. Ideally, it would give you links to like the exact span of text in the evidence that was used. But I didn't want to bother trying to figure out how to prompt engineer it to do that. So here we see the question, the same question as before. And now we see this evidence. So this is what I retrieved, this article. I gave it the title of the article, the author, the date, and the URL. And then I could just paste it in the entire text of this article. And then I said answer colon. So this is literally how these things like Bing Chat and all work. They have a template, they put the retrieved evidence from like normal Bing search into this template, and then they pass it into GPT-4 to generate an answer. There's nothing fancy about this system, but you can imagine as you collect human feedback data and tune GPT-4 to better be able to understand how to handle this evidence document and how to cite it properly and so on, you start to change the behavior of the language model in such a way that it's better able to interact with the evidence. All right, so let's see how this works. Imagine a thunderstorm is a big angry cloud with lots of electricity inside. So far it has not cited the evidence article. Oh, here we go. It now is mentioning the US Center of Disease Control and Prevention, which was mentioned in the evidence document. However, it did not cite that, but perhaps this part, yeah, I don't know what this, maybe this was some sort of citation. Typically half an hour after hearing that final thunderclap is a safe time to venture back into the shower. Does it say it somewhere in here? Oh yeah, it says it right here. So it did copy directly from the evidence document. However, it did not provide a citation like I asked it to, although maybe it thought that this is a sufficient citation, just like quoting it, but yeah, there's no, oh, it did that here too, okay. Interesting. So this is a new citation format to me, but I guess it works. Also, this is only 3 paragraphs long, so note that it didn't actually follow my instructions. I could do this again and see if it, okay, little buddy. I guess because I said explain to a 5-year-old. Oh, so here's an actual citation of the article with just the author and the year. Okay, did it. So this is obviously not a great citation format either. Okay, well, it's going overboard on the citations, but overall, like, this is, you know, at least different behavior qualitatively than what we saw without the evidence document, right? And so you can imagine changing your prompt many times in order to tweak this so that the output is actually, you know, acceptable to someone who's who wants to answer. Okay, so yeah, one thing that I wanted to say is that when you're integrating these kinds of retrievals or other information into the prompt, you could imagine sometimes the retrieval might not be in the form of text. It could be like a table, or it could be some sort of structured data, right? In that case, like, the model may not know how to reason over the text in the prompt, and so you might have to provide it few-shot examples of the form query, evidence, answer. You might have to actually fine-tune it, or you know, get some human feedback and tune it with RL, which is only possible if you are OpenAI. But this isn't just like a general purpose solution, right? If your evidence is very long and complicated, the model may not be able to reason over it properly. All right, any questions about this? Okay, yeah, it's relatively straightforward. What is the difference between zero-shot and instruction tuning? So in zero-shot, I could just give it the question with no further instructions and ask it to answer. With instruction tuning, you additionally give it instructions on how it's supposed to answer the question, which could be very detailed. But they are very similar. Okay, so yeah.
Are instructions preserved in any kind of state? Like, I know specifically saying, we'll do GPT-4 here. You can open up a dialogue.
Right. Right.
So would you be able to use instructions from earlier on?
Yeah. So I could just have this input, have it generate an answer, and then say, you know, what was my format here? oh, I would have to give it another question and evidence, and ideally it would use the same format to, and I think it would because it's very clear from this essentially becomes a demonstration to GPT-4. Yeah. Okay, so we have 10 minutes left, and I think a couple more things I wanted to show. So the next thing I wanted to talk about was chain of thought prompting, which we already looked at briefly before when he talked about like emergent properties of these large language models. I wanted to give a quick demonstration of this, and now we're going to use a math word problem since these are the types of problems for which chain of thought prompting initially became popular. So here we have a question. Marty has 100 centimeters of ribbon. He must cut into 4 equal parts. Each of the cut parts must then be divided into 5 equal parts. How long will each final cut be? So in zero-shot chain of thought prompting, we don't give it any examples of the reasoning that the model has to do in order to solve this problem. Instead, people have found that if you just say something like, let's think step by step, the model will output the steps of the reasoning that it takes and then produce the answer. So let's see what happens here. Okay, so it says first he needs to cut, so it's doing the first step of this, the first division. So now it finds that there's 4 equal parts that are each 25 centimeters. Now each of those needs to be divided into 5 equal parts, so it does this other calculation, and then it gets the final answer, right? So it's not just outputting 5 centimeters, it's outputting the steps that it took to do this reasoning. In chain of thought prompting, and this example is just from the blog post that I gave you, you actually give the model examples of how it should reason over these questions. So here, there's this question about Tom and Elizabeth, and if you see in the answer, there's actually some sort of reasoning that the model should do in order to solve this problem, and it's written out in some format that the model should solve. So here I imagine this is a simple question, the model will get it right. So you can see it's using the same format as the demonstrations in the prompt, right? These are just demonstrations that are in the prompt, but you can see that the answer is not just the final answer, but it has these steps of reasoning. And so chain of thought prompting was shown to be present. It's actually useful in large language models because their performance improves on these math word problems when they're actually forced to write out all the steps as opposed to just produce the final answer. Okay, so we already talked about this one, so I won't dwell over it. So the last one of these strategies that I want to try out in the playground is called self-consistency prompting. So this is a very simple technique as well. Basically, what it means is you take the question, you know there's some randomness associated with the answer, so you generate multiple samples, and then you take the answer that, you basically take the majority vote answer, so the answer that is most commonly output across all of those samples. So I was having a hard time finding a hard enough question. So this is from the Putnam math competition this year, so hopefully the model wasn't trained on it. Oh, that formatting is pretty bad. Anyway, it says, answer the question as concisely as possible. Alice and Bob play a game on a board consisting of one row of 2022 consecutive squares. They take turns placing tiles that cover 2 adjacent squares. There's a lot of rules to this game. This problem is not easy at all. And the answer to this question, according to the solutions of the competition, is 290. What is the greatest number of uncovered squares that Alice can ensure at the end of the game, no matter how Bob plays? So the correct answer is 290. This is the actual way to solve the answer. You can see that it is extremely long, requires many steps, and is far beyond the capabilities of GPT-4. Especially if I say answer as concisely as possible, but let's see what happens. The greatest number of uncovered squares that Alice can ensure at the end of the game is 2. Okay, so I might take this sample as the answer, but in self-consistency prompting, I would instead go back and resample an answer. Okay, so this time it's 674, so there's a pretty wild range here. Maybe I'll do it again. Okay, so I took 3 samples. One time it said 2. The other 2 times it said 674. So I would take the majority vote, which would be 674. Obviously, in this case, it's still wrong, but this is a hard problem. I don't think many of you probably would struggle to get this this question right. So yeah, but you can also make it kind of give its list of how it came up with this answer. I tried to cut that because it was generating a lot of stuff and it was always wrong. So anyway, okay, so this is just a summary of some popular techniques for getting improved performance out of these models for various tasks by prompting them. I wanted to finish by talking about a couple more interesting augmentations of these language models. So this was one of the optional readings for today, this tool former paper. I just wanted to cover briefly how it works so you can look at the figure here to understand. But essentially, this paper is very similar to later products by OpenAI, namely their plugins that they offer with the ChatGPT, where the language model can interact with external APIs to do a whole range of new tasks that it couldn't do when it's just outputting text. So here you can see that the model has these colored expressions here are API calls to some external API, like calculator. This means that there is some calculator function that takes in arguments like this, and if the model ever generates something like calculator 400 over 1400, instead of making the model do this math, this is sent to the calculator function, which can just easily compute this, right? So you might have seen ChatGPT's integration with Wolfram Alpha. This is very similar, right? The language model will generate text and API calls. And once the language model generates this the sequence here, the API calls that it generates can be executed, and then the text in the corresponding text can be filled in. So here you see out of 1,400 participants, 400 parentheses or, and then we have this API call that's trying to figure out the percentage, like what is 400 over 1,400, pass the test. And so once I generate this, I can then run the calculator call to get 29% and fill it in. So what is the advantage of doing this in the specific calculator example over just having the model produce everything at once? Yeah, so we can make it do things, interact with, there's already so many APIs that have been built for many services, right? Like, restaurant booking or travel booking or, computing various mathematical functions, right? All of these are in the form of API calls. And so if we teach the model how to use these API calls, then it can potentially be deployed in a lot more use cases. Yeah, so real-time data is another thing, right? So here, you can see this other API called this QA API, who is a publisher of the New England Journal of Medicine. This could get sent to Google search, right? And then you could get an output and then put that into your final output that's generated by the language model. You can see here there's a wiki search function. There's a translate function here. So maybe your model is trained on only English, but you do want it to have some translation capability. Maybe you can just outsource that to some external translation module, right? So this kind of augmentation of language models with external APIs is kind of generalizing the retrieval augmentation, right, to many other types of external functions that the language model could do. So if you wanted to make your own tool former, it's actually quite simple. You just have your relevant API calls that you're interested in, and then you just have to define them in your prompt. Like, you have the ability to use this calculator function or this Google search function. Its arguments are like this. You don't have to actually train it or anything like that. I think in this work they do some training, but for example, in ChatGPT's plugins, these are just basically implemented by cleverly engineered prompts. There's no modification to the model behind it. They just list out the API commands, maybe some examples of how to use them, and the model figures it out from there. So as you can see, these models are very flexible, and probably in the future they'll be deployed in cases where they can actually carry out instructions by generating API calls and then having an executor. As you can imagine, this also comes with huge risks, right? What if they hallucinate something and generate a terrible API call with huge consequences? There needs to be some safeguards, right? So probably we won't see this right away, but who knows? So yeah, I guess, so just to wrap up, next week is the midterm week. So on Monday, we will talk about the previous exam questions, and I'll answer any questions that you may have. And then on Wednesday, there will be the exam. So I'll also put this on Piazza, but we decided the exam time frame will be 2:30 to 6:30. So starting from when this class starts, extended 4 hours. So you get a 4-hour block to turn it in on Gradescope. It'll be remote, so don't come to class. And for those of you in the online section of the class, we'll have a time frame 4-hour block later that evening for you to do it. But yeah, so make sure to carve out some time. The exam won't take all 4 hours, but I know people like to spend the whole time anyway. Just make sure you're free during at least 2 or 3 hours of that block to complete the exam. All right, so good luck on your preparation, and see you next week.